Hi, my name is Iban, and I will present the paper Formal Schedulability Analysis based on multi-core RTOS model. The work has been done with Jean-Luc Bechnek and Olivier Henri Roux as part of a PhD thesis project with Huawei. This work is about schedulability analysis, so about verifying a real-time system using model checking. We are going to know if tasks respect their deadlines, under which temporal conditions the application is schedulable, and we want to automatically compute the response time of a task. For this, we consider a detailed model of a multi-core operating system and a real-time application with dependent preemptive tasks. We will use high-level Petri net with stopwatches for modeling both the multi-core RTOS and the application. And we choose this formalism because it is better adapted to the parallelism we find in a multi-core system. We are going to apply our approach on trampoline RTOS. It is a small embedded system aligned with OSEC and AUTOSAR standards. The goal now is to verify the schedulability properties based on a complete model, and every trace that contradicts the property can be detected using the model checker. The use of observers allows to reduce the verification problem to a verification of reachability properties. So the basic overview of the presentation is first an introduction to trampoline RTOS and the chosen formalism. Next, the presentation of the modeling rules concerning the RTOS and the application. And then the formal verification and obtained results for two case studies. And finally, the conclusion and our future work. So first, let's turn our attention to trampoline RTOS. The operating system chosen here is trampoline. It implements fixed priority partitioned scheduling. And this type of scheduling consists of statically allocating the set of tasks to a processor. Trampoline is composed of three layers in its architecture, as shown in the figure. So the API contains all the services available to the application. Then the kernel contains all the low-level functions on which the trampoline services are based. And finally, the BSP, the board support package, is the low-level part of trampoline depending on the target machine. Modeling is done with high-level stopwatch Petri net formalism. And the high-level Petri net, known as a place and transition net, it is proposed for a modeling system with complex structures and to manipulate different types of expressions that use state variables. And by adding the notion of stopwatch, the time associated with a transition can be suspended and later resumed at the same point. Here we consider a Petri net model which encompasses both stopwatches and high-level functionalities. This example is the modeling of the preemptive scheduling of two tasks with counter. We have the first task here is a periodic one, and the second is also periodic, but it is executed only 10 times because we have a counter. The scheduling is captured by the derivative function of the stopwatches called is running and associated with C1 and C2 transitions. The initial marking of the example enables the transition T1 and T2, and a marking of a Petri net is a vector that represents the number of tokens of each place. And a transition is enabled if there are enough tokens in its input places for the conception. And if we fire a transition in a marking, we consume one token from each of its input places, and we produce one token in each of its output places. So here we have transitions T1 and T2 are enabled, and after 10 time units we can fire the transition T1. So we will fire the transition T1, and this leads to a state where the derivative function of the stopwatch associated with the C1 transition is equal to 1. This allows the time to elapse for task 1. And after 5 time units, T2 is fireable, and in this state, the derivative function of the stopwatch associated with the transition C2 is equal to 0, meaning that the task 2 is preempted by the task 1, and the time associated with the transition C2 is suspended. So now let's move to system modeling. So the foundation of the modeling is built on bases. First, the structure of the Petri net describes the control flow of the operating system, and this is possible because Petri net allows to associate to each transition a set of imperative expressions. The variables used in the model are those of the operating system, and also the actions and conditions on these variables associated with each transition are the same of the operating system program. The code associated with the transition corresponds to an interpretable operating system code which guarantee atomicity. We start with the RTOS model that we built from its C source code. The entire RTOS is abstracted by a Petri net that describes the control flow of the operating system. Also, the firing time intervals are all set to 0, so time does not elapse within the RTOS model. And function call is made by dropping a token in the initial place of the Petri subnet modeling. In this example, the function f call g, so we produce a token in this place, and we wait via a guard for the final place to receive the token. This indicates that the function g has completed its execution, and when it happens, the final place of the called function is emptied. The application model is built from application source code and its OIL description. We extract from the OIL description the model variables such as the properties, periods, core on which task runs, and so on. Tasks are modeled by a sequence of system calls such as activate task, terminate task, with the execution times in form of an interval between the best case execution and the worst case execution time. Here we have a modeling example of a multi-core application as shown in the figure. This simple application consists of 3 tasks. Task 1 runs on core 0, while the other 2 tasks run on core 1. The scheduling is controlled by the OS model, and when a task is scheduled and the OS is not running, the function is running returns 1. That allows the time to elapse. Otherwise, the function returns 0 and blocks the elapse of time. So now we will move on to the verification approach. So in the verification part, we form a chain that includes the steps shown in the figure. We use observers that allow to reduce the verification problem to a verification of reachability properties. And we model and verify our system using a Romeo tool. So Romeo allows the model checking of a TCTL property over a high stopwatch between nets. We can also use parameters in the time interval, and Romeo synthesize the values of the parameters that guarantee the property to be true. And the first step was the modeling of the observers. So the observer model is represented in yellow in the figure. We linked it to each task model and cannot interfere with the system. The delay di represents the deadline of a task I. The firing of transition OK means that the task terminates before its deadline. The firing of transition deadline means the task does not respect its deadline. So the place ops is emptied at the end by the transition to avoid tokens accumulation. And to verify schedulability property, we check that for all states of the state space, there is no token in place ops with the formula written in CTL. We can also replace any interval bound by parameters. Romeo will synthesize the set of values of the parameters such that property is true. So we can parameterize an execution time, and Romeo synthesizes the value of the execution time such that the task respects its deadline. Or we can parameterize the deadline and Romeo compute the response time of the task, the time between the job activation and the end of its execution. Now let us consider the same system presented previously with the characteristic of the table. The application consists of 3 tasks. Task 1 runs on core 0, while the other 2 tasks run on core 1. We add 1 observer per task, and only task 1 have a time interval. If we consider, for example, its execution time is equal to its worst case, equal to 11, we found that the task meets their deadline, but we now ask for the whole execution time interval of task 1. And also the result is verified using a Romeo tool that allows to run the time traced and give us the chronogram represented in the figure. So as shown in the figure, all the tasks meet their deadlines. So for the scheduling analysis, considering the whole task execution time interval, we verify the schedulability property, and a counterexample execution trace is generated since this property is not satisfied by the model checker Romeo. That proves that task 3 can miss its deadline for the best case execution time that is equal to 8. Task 3 running on core 1 does not have the time to finish before its deadline. We want now to synthesize the task execution time for the task 1 that allows the task system to meet their deadlines and then to be schedulable. So we set the first execution part in the parametric interval AB and we bound parameters by 11. The Romeo synthesis shows that the execution time of task 1 must be between 10 and 11. So we have run a full analysis of the application with the RTOS, performed in the first time using no parameters to verify schedulability, and in the second time with parameter synthesis to find the execution time interval of task 1. And since the multi-core version of Trampoline implements fixed priority partition scheduling, we are asking if new scheduling policies can be implemented within the RTOS. Can their behavior be formally verified using model checking? So the answer is yes, and we implement and verify an ad hoc scheduler in the following. So first we define the scheduler and provide the scheduling specification. The application consists of 4 tasks. Task 1 and 4 are assigned to run on core 0, and task 2 and 3 are assigned to run on core 1. The activation and termination of task 1 and 4 on core 0 lead to rescheduling task 2 and 3 on core 1 and priority inversion of task 2 and 3 on core 1. So we construct the application model with the characteristic of the table, and we apply verification chain using Romeo model checker tool. Our task model are linked with the observer, and to analyze the response time of task, we just replace the deadline with a parameter in its observer, and Romeo synthesizes the values and provides the result shown in the table. The response time of task is the smallest value obtained in the table. So if we instantiate the deadlines with their values in the observers and verify the schedulability property, Romeo replies that the property is not satisfied and automatically generates a time trace as a counterexample represented by the chronogram in the figure. So in this case, the response time of task 3 is equal to 12 and is greater than the deadline of the task 3. So as we can see in the chronogram, task 3 is preempted twice by task 2, so it misses its deadline when its execution time is equal to the worst case execution time, equal to 6. So we replace now the task 3 and 4 time interval by a parametric one in order to find the task's execution time interval such that the task meets their deadlines. And after checking the schedulability property, we obtain 2 results with Romeo synthesis. So the first result bounds the parameters in an interval And the second result provides a relationship between parameters. So to verify these results, we use the simulator of Romeo tool that allows to run timed traces, the chronograms. So the first result is verified with the value 3. It's the best case execution time for task 3 and 4. And in this case, task 2 terminates its execution, whereas the first job of task 3 is terminated. And the second result provides a relationship between the parameters A and B, such that A is greater than B minus 1. This property is satisfied with the 5.5 value, and so we set this value, and and the extracted time trace is presented in the figure obtained by Romeo tool. The task set is therefore schedulable for this value. So to conclude, a complete model can be used to check the schedulability of an application and task response times. It also allows in its parameterized version to calculate the execution times required to guarantee schedulability or response times. And in the next step, we aim to model the multi-core version that allows parallel execution of the kernel code on different cores, and to verify also the alignment to the AutoSAR standard. We will also evaluate the approach scalability and how it can be used for a bigger and more complicated system. So thank you for your attention, and if you have any questions, please feel free to ask. Thanks.